Okay, so our next presentation is from Scott Cray, who is here at the University of Minnesota 26. Go ahead.
All right, I have one sec. Let me get Zoom out of the way here. Okay. All right, so my name is Scott Cray. I'm going to talk to you about Olympo, a balloon-borne instrument to probe galaxy cluster structure formation. And my advisor is Shaul Henny at the University of Minnesota here, and I'm a first-year grad student. So a little bit about the background of the science we're studying. So we're looking at galaxy clusters, and specifically the largest scale structure formation of galaxy clusters. To give you an idea of the scale, you can see a typical galaxy in the upper right here is about 0.05 megaparsecs, or 163,000 light years across. Galaxy clusters being much bigger, hundreds to thousands of galaxy clusters are about 2.2 megaparsecs across. And we're looking at this galaxy cluster scale for our observations and trying to figure out how they form and confirm theoretical models of galaxy structure formation. So in this center plot here, you can see at these purple nodes, these are theoretical models, not observations, of galaxy clusters, and you know there's many galaxy clusters at each of these nodes, or excuse me, well, I'll get back to that, but there's filaments that connect each of these galaxy clusters in large vacuums of empty space in between them. So we're interested in the gas flow dynamics at the outer extents of the galaxy clusters, or these nodes that you can see here. And to look at this, we're actually proposing, and this is a proposal of designing and building a telescope to look at these regions. And so Olympo is this telescope. It's a balloon-borne telescope, and the idea is that we would directly observe gas flow of the galaxy formation. And to do that, we need to see from the central region of the galaxy cluster all the way out to 1.5 megaparsecs in distance. And that's farther than any other observation to date. So this is a key thing to observe the actual gas flow that's collapsing in these regions to form these clusters and filaments. And the second goal then is to search for missing baryons. So there's a discrepancy between the expected baryonic mass that we have today and the baryonic mass at the Big Bang by about a factor of 2. And one possibility is that all these missing baryons are in the low density gas regions at the outer extents of galaxy clusters. So for measurement principle, so how do we do this? So we use something called the Sunyaev-Zeldovich effect, where we're looking at the photons from the Big Bang at the CMB background radiation that's coming toward Earth from every direction, as it interacts with hot ionized plasmas in the galaxy clusters. It does something called inverse photon scattering, where the hot plasma actually adds energy in a particle collision with the photon and energizes it and shifts the spectrum. And we can observe that shifted spectrum in the CMB, and then you're taking a inferred measurement of, there must have been hot plasma in between the background CMB and what you're observing, and that's how you're mapping mapping the galaxy cluster. In addition to that, we're combining the data with X-ray data from eROSITA and GRISM, and together with all of this data, we can map together everything that we need to accomplish our science goals. So the next logical question is, why not do this from ground-based methods? There are ground-based observatories that can measure in millimeter wavelength, and thus perform this SZE, or Sunyaev-Zeldovich effect measurement. However, on the large angular scale size, such as galaxy clusters, atmospheric turbulence prevents continuous measurements that provide a coherent measurement that's useful for making these observations. So a balloon-borne observation is a great way to solve this problem. Obviously, space would be even better, but then it's extremely expensive. So a balloon is a sufficient solution. So to do this, we're planning on using Olympo. Olympo is an already built telescope, or gondola is the term for the payload that's underneath the balloon. We're going to modify it in many ways. The instruments, the range of motion, the shielding, many other things, the detectors. And it's a 2.6 meter Ritchie-Crescent telescope that observes in 4 frequency bands, all in the millimeter wavelength. And it uses something that's a little bit newer for detectors, these kinetic inductance detector arrays. You can see them on the bottom right. There's one that's a wafer, and then an individual detector is shown on the right of that. In the middle, you can see the Olympo gondola. This has already been in the state that it's had a test flight. And then on the left-hand side, you can see the optics, the cryostat, which these optics and instruments are cooled down to liquid helium around 4 Kelvin type temperatures to reduce thermal noise. So the proposed flight plan would be in Antarctica, starting in McMurdo, and last for about 30 days. And you can see below is an example from a different flight, Anita, that I just pulled from NASA's website. And you can see the path of around 3 times around the South Pole is what this is mapping. So the blue is the first path, the green is the second, and then the red is the third. And our flight would probably be something similar. So the work that I'm specifically doing on Olympo is the next 2 slides. Again, this is all in the proposal phase, so we don't actually have funding for this, but we're working on getting funding. And so the first thing that was needed was to improve the elevation range. So for our science goals, we needed to be able to observe at near 60 degrees elevation, which exceeded the previous elevation range of around 45 degrees. So I found a simple solution to this problem by just separating the existing frame right at the flanges and inserting this spacer that you can see right here. So a nice, simple, elegant engineering solution. We don't have to make modifications, just unbolt it, make a new fabrication and bolt it in. Then I performed FEA analysis on the 2 loading considerations to verify its flight worthiness. There's a 10G vertical acceleration requirement and a side load requirement, which I don't have shown here, but this design meets both those requirements. So it seems like a nice, easy, and good solution that still meets the flight requirements. And the second thing I worked on was the shielding. So after modifying the elevation range, and then also adapting for our different science goals, we have different sun shield requirements and also earth shield requirements. So I created a simulation in SolidWorks. You can see this on the bottom left, where this is just a blocker or a shield. And this in the upper left is a light source. And then I'm just looking, I'm changing the model, and I'm changing positions of the Antarctic sun, which is about always at 35 degrees during December. And then looking for any light. So we don't want any direct sunlight or secondary sunlight that can be incident on the primary. And we don't want any earth shine, any direct earth shine on the primary either. So this is the end optimized design that I came up with, where the pink or reddish color is the sun shield, and then the bluish turquoise is the earth shield. The entire inner frame then can go up and down for elevation, and it still maintains its earth shine and sunshine shielding. So the design, at least at a preliminary level, seems to work. Certainly, if we get funded and we're actually going to design and build this telescope, there would be more thorough analysis, but proof of concept, this looks really good. So in summary, Olimpo is a proposed balloon-borne telescope designed to observe galaxy cluster formation, gas flow, and determine masses of gas in low-density regions to search for missing baryons. And I've developed concept designs that allow for improved elevation range and shielding to enable observation of targeted galaxy clusters. So if anyone has any questions or thoughts.
Okay, thank you.
I have a question.
So Demos has a question.
All right.
Nice talk. So I'm trying to figure out the 10G requirement for a balloon flight. Is
Yeah.
it for the ascent or for the landing?
Yeah, it's for the
Landing.
ascent. It's for the ascent, and there is some factor of safety there. So I don't think the actual intended load is a 10G acceleration load, but that's the requirement from the launch requirement is a 10G acceleration, and that you have to show that it meets that requirement.
That's a lot more severe than I thought a balloon flight would have, but well, that's interesting. All right, cool.
Yeah, so one thing to keep in mind is the size of these. I think the payload is I forget the exact amount, but on the order of maybe 2,000 kilograms or something. And it's very, very, very large helium balloons. So these are big, expensive operations, and I think there's probably a pretty healthy factor of safety there.
Other questions? I have a question about the existence of this device. You said more than once, you have this as a proposal, and yet you also said it exists and it's already flown. It's like, I don't
Yeah.
understand what's been proposed. A retrofit of an existing experiment or something?
That's exactly right. It's a retrofit. So the base, if you can see here that this base gondola exists. It's taken a test flight. It works, but it's probably, I don't know the exact date, 15, 20 years old. And it didn't have the same science goals, obviously. So we need all new detectors. The optics are going to change. The secondary optics past the secondary mirror. So inside the cryostat, we need to make some cryostat modifications to extend the liquid helium to keep it cold. So we need a larger liquid helium capacity. So there's quite substantial optics upgrades, detector upgrades. We're going to change the gyroscopes to get state-of-the-art gyroscopes. The computer system's old, so that needs to get replaced. I'd mentioned the elevation range, the shielding. So we kind of have a base platform to start with, but a lot of the specifics and details will be new.
Okay, last chance for questions, anybody? Yes, go ahead.
So I thought,
Not too close.
I thought the missing baryon problem kind of was solved already. So what is this experiment gonna add to that?
I don't know. Maybe you'll maybe have to inform me on what has been solved. I guess as far as I'm aware, there's still a missing factor of 2. For missing baryons. Maybe that's news to me, but that's what I'm aware of. And I'm far from an expert at this. I'm a first-year grad student, so.
Yeah, I just heard from like Pop Science, but there's Wikipedia and resolution from 2017. So, but it maybe it's incomplete. So I was just wondering.
Yeah, it's a great question. I wish I could shed more light on it. I just don't have any more information.
Why don't you introduce yourself so that you can keep in touch? Who's asking the question?
Yeah, my name's William. I'm a third-year grad student, so I work on tape 2.
Oh, okay.
You're giving a talk later.
And I'm giving a talk, and I do with solar detectors, so we can chat. Yeah.
Nice solution.
Okay, thanks again, Scott.
Thanks.
Another hand.